Now I'll come to the slide I already showed you. So here's the quest. In fact, it's not quest, it's questions. So the questions that I will use just to finish this mini presentation is where do we really benefit from the alchemy, the way that the atomic physics people are simulating condensed matter physics? Where do we benefit from having the superconducting community simulate quantum optical effects that have actually been in the textbooks in quantum optics for 30 or 40 years? Are you just beating us in our faces because we didn't succeed as well as you do? Or where's the next step for that kind of research? So that is one discussion line. Another discussion line is are there other goals than these, which may really be pursued with the hybrid systems or beyond? Okay, so this is my question. Let's finish on the happy note of the happy greeting from Serge Roche, but then let's have a discussion to see if we actually deserved it. So with that, I'm not going to ask a provocative question, but maybe somebody has a view on some of these ideas. And we have a couple of microphones in the room. Yes, please. Olivier.
Here's a provocative question for you, Klaus. Been working on continuous variables and entangling fields of light for 10 years now. It's nowhere in your talk, so what do you think about it?
Oh, of course it's in my talk or in this brief presentation. So of course in the brief presentation it's there because we have the photons and it's clear that when we come up in the hybrid scheme, we will even have different modalities of the propagating fields. They can be propagating photons in a continuous wave, or they could be single photon Fock states, the optical cavities and photonic structures on the left. So of course the photons are a genuine part. I think we also learned now that the superconducting qubits, sometimes it's actually the microwave photons rather than the plasmons, which are the good storage elements. Maybe the cavities are the better information holders in the superconducting devices. So of course it's all there. It's all there. But of course it's a question to you. Where do you think it fits in?
Well, I think there's a few groups in the world who think that you could replace qubits with Q-modes.
Yeah.
Right. And the scalability of the entanglement is actually the record for these. Yeah. It's the biggest that you can get. Furusawa got 1 million entangled Q-modes in a cluster state. Right. Which you can do quantum computing on if you have the right performance. Regarding fidelity, right, you do one thing at a time, you do scalability first and fidelity second. Most other platforms have done fidelity first and scalability second. But I think these are also some things that you want to consider, and people who work on superconducting qubits and nanomechanical oscillators, optomechanics, are looking at other bosons than photons, phonons basically, and you can do exactly the same thing with them, of course. Yeah. So I think this is a whole area there that's been, and we know that there is a fault tolerance threshold for continuous variable quantum computing. Right. We've known that for 2 or 3 years, so it's pretty recent, but it's not like it's impossible to do with that. So sure. So we, first of all, we look forward to your presentation on that, of course, at this meeting. And you would actually say that it targets all the way to the top of these goals. I mean, it's for the fault-tolerant quantum computing that you see the entangled photon. There's no no-go theorem against it. No, good.
So I want to make the distinction between sensing and all the rest, because I think also related to the previous comment, maybe 10 years ago, hybrids seemed like the standard computing model of a processing unit and maybe a memory of some sort, like a hard disk, which was magnetic. And then you would have that best of both worlds. But the task of doing high fidelity coupling has killed a lot of those attempts. And the best people have tried very, very hard and have not succeeded, at least to the level that is competitive with the single platform implementations. However, in the sensing and also in the communications aspect, I think to a certain extent that's very different. So I wanted to put that emphasis that there, even lower fidelities, which we have in these hybrid systems, by definition, because I think it was Jörg Schmidmayr in one of his talks that I heard years ago said it's the worst of all possible worlds. This is like a Voltaire statement. When you bring these things together, it doesn't always come out the best. Usually it's the worst because of the natural conflict you placed between these systems of working and scaling. So just that point about the communication and sensing being really truly different, and their hybrids are probably the most promising option because one is a sensor, the other one's some error correction, enhancement, probing of that, which even without fault tolerance can already give you the advantage.
Yes. I agree very much with that. Actually, I was in a network some years ago. They wanted to interface single ions to superconducting qubits. And I said, well, the first thing you're going to do is to see if the superconductor qubit can at all sense the ion is there. And then you're going to write your first Nature article about that. Then if the ion can also see the superconducting qubit, you have got the second one. So, and of course, it is true, some of the groups we are involved in a project also with Saclay, where the idea of storing the microwave photons into spin ensembles is hard, but something still pursued. But sensing the spin ensemble using the microwaves, that's a very interesting prospect. Jörg, please.
Maybe I want to answer to that.
Yeah, that's good.
So yes, in principle it's very difficult, and you might, in principle it's very difficult, and you might, ask the question: is there a possibility that a combined system is better in all aspects of coherence, for example, than the separate systems? And there is a paper which Johannes Meyer, one of the guys in my group, he led a group on superconducting circuits, and NV coupling, where he basically showed that, every system in its own had coherence times that are much shorter than a microsecond, and they stored in a spectral hole. They stored the stored waves that you put in there has a lifetime, has a line width of 100 kilohertz.
Yeah.
So it's basically a factor 10 better, and he could store 4 different things in a different part. So in principle, it's possible to make it better by an order of, at least in this simple system, it's better to make it better by an order of magnitude than each of the separate systems. Yeah, so the lifetime was much longer than a lifetime of the photon in a cavity and things like that, of the
Yes.
stored system. So, but it's hard, it's not straightforward. And of course, you pick a different system, and it's still much better than what we achieved there. But for these two, combining these two things, this became an order of magnitude better than each of the subsystems.
So just to clarify, I mean, I was describing this hybrid thing very much as a modular thing. You shuffle thing to the other place, do the gate here, store here. But what Jörg is referring to is that by coupling these systems, you might actually
Create new
distribute the
states.
properties. And that is when we wrote this paper, Gershon wanted to have a whole section on real hybridization, which is actually not having a system composed of 2 subsystems, but having them interact and getting the properties of this new emerging technology. And of course, we should think as physicists like that coupling these systems, you might do exactly what Jörg referred to, get longer coherence times because the coupled system features gap states or some other property. Yeah.
So I'd like to pick up on that because it brings me to something that was developed within the superconducting community, which is called Blackcom Quantization. And I think I don't know if everyone is familiar with it. It's a language in which you study the interaction between systems, including hybridization, in terms of impedance matching and the language of electrical engineering. And that's good if the coupling is moderate or weak. And at least in these schemes, and not true hybridization that you mentioned, in these schemes it's typically some sort of weaker coupling. And there you can do a linearized electrical engineering, which is the poor man's version of the matrix element, but it gives a huge amount of intuition. And I think what's missing to understand whether these things will actually work is intuition. So maybe that language can help others.
I think that's exactly right. And I mean, from Jörg, the story was essentially having a strong coupling that gaps some excitations in a system, and then your state gets protected. And we come with different stories from the different fields, and maybe we have to do a little more storytelling about what are our tricks. I mean,
about intuition, maybe Klaus used to say, when we were writing this paper, we wanted to give a general way of making a figure of merit how good the system is, and we miserably failed.
yes.
Yeah. We really miserably failed to come up with a general way of quantifying these type of systems. or that delayed the paper by quite a while because we said, damn it, we have to come up with a nice way of getting a nice figure of merit of putting in how good these systems are. And we basically, you know, and I think it's up to now there's no general figure of merit. No? We, you know.
Yes, another question?
So I'd like to share a personal debate that I've been thinking about as a young researcher doing theory, which is how much time and efforts do we want to spend in the applicative side of the problem? I mean, so should I collaborate more with my friends that do experiments to understand what is the figure of merit of a theoretical model, or should I work more with my friends that actually do a device that has a squid and can measure magnetic fields? You know, we do have already sensing, but we could do it better. So, you know, am I a physicist or am I an engineer? After all, I have only 24 hours a day. So.
That's a good question, and we also heard that the industry is now ready to take over where we stop. I mean, of course, we heard also a request that we should still be in the background and provide input for the same industry. But I mean, where is that division going to be in the future? Did I see Dieter? Measured.
I can share this experience of trying to come up with a figure of merit for certain systems. We tried something similar for quantum repeaters, and the same thing, we miserably failed. And I think the reason is if you look into this slide and the other one, if you just flip back and forth between the two, then you see this is what we do currently. We talk about superconducting qubits, nuclear spins, mechanical resonators, some photons here and there. And I think the transition, at least from my point, we have to start thinking from the system point of view. In my view, the technology is not going to make progress unless we start talking and thinking about the system, because only then we will see what connections we really have to do. As long as we stay with our component or so, we will just walk in everybody's out of phase with everybody else and so on. And so I think the systems are going to be complex and more complex, and we need to think about this, and perhaps physicists are not the right ones to do this. We may need many more engineers in this who are better adapted to this job.
Yeah, so maybe that also relates to Emmanuel's questions, because it's really, I mean, I guess there are many people working on one of these systems who think this is really fun. It's cool that I can refer to this big picture, but in fact, I don't care. I go into my lab and then I work on this fantastic system. I hope I'm not offending anybody. So, I mean, are we all saying the same thing about what we do in the lab when our sponsors are present and when our sponsors are not present, and why we do it? And at least I exercised a little bit with myself. I mean, I like to be honest, so I like the thing I write in my applications, that's also what I tell the students, this is why we do this. And that's an interesting exercise also. And you want maybe to think out of the box, but you can also say that my expertise is to develop this box so that it fits with the other people's boxes, of course. Yes?
So I have a question. Maybe some of the condensed matter colleagues can answer. When we look at the goal chart that you've shown, then full-scale fault-tolerant quantum computing is very, very, very difficult, and perhaps quite a few years ahead of us. And there are several, maybe not too many, well-defined goals that we know that if we can achieve them, we can outperform, as far as we know, classical computers such as Grover or Shor and so on. And I think most people would agree that quantum simulations are a much simpler task to go after in the intermediate or shorter term. And looking around, people are trying to simulate, for example, spin Hamiltonians that are uneasy to solve as we go to more and more larger number of spins. What I'm at least unclear about is, what are the golden eggs that we're after? The equivalent of a Shor or a Grover algorithm in the world of a quantum simulation, because clearly, let's say we could follow up, without any exponentially small gap to the ground state, trying to verify that it is indeed the ground state is an exponentially difficult task. So of course, that's not what we're going to be after. We're going to be after some correlation function or some average quantity or some order parameter. So what are the things that are beyond classical calculation, and even at a even different layer, what are the things that are then equivalent to some computation problems that are interesting and a bit more universal or general than the specific 10th order correlation function of some Hamiltonian. So where does it come useful?
Yes. Yeah, please.
So maybe partially address this. Maybe to partially address this concern, if I do this quantum simulation and I reach some result, I don't need to verify it in a sense because I will use this result experimentally in the lab to produce something. And this something will be helpful for me. It could be medicine, it could be better nutrition, it could be anything else, or maybe something destructive, maybe some powerful TNT. But the point is that I cannot produce this medicine upfront today because I have so many possibilities to do in the lab. And if I use this quantum simulation and reach the best possibility, I can go ahead and test it in the lab.
How do you know that you can believe the simulation?
I'm sorry?
How do you know that you can actually believe the simulation?
No, this is a different question, at least from what I understand. Therefore, I'm only partially addressing it. I don't know if the simulation will work. But if it will work, I don't need to verify. The question was, okay, suppose I do a quantum simulation, how do I know it is work? Because I cannot simulate it in any other way.
So it's molecular structure you're after, basically.
So we have a comment for you.
So maybe not necessarily a comment, but another question or research agenda. It seems quite clear that nature, not in the engineered sense that the systems that we build and isolate so very, very carefully, that nature is using quantum mechanics in an entangled sense to a certain extent. But how big is that extent? Natural materials, how complex are they? What are they in the sense of how big is the Hilbert space that is actually being used? Maybe we're just not clever enough in our diagonalizations, in our choice of bases. How rich is nature? Even in the protein folding problem, how many bits or complex is the computation that nature is doing in order to fold? So that relates, I think, to Roi's question, because that would answer how hard we have to try with our engineered systems.
I want to make a more general comment, also related to the golden eggs. Where are they? I think the best part of it is that nobody knows. Otherwise, everybody would be rushing there. It would be a gold rush, and we know who wins in a gold rush. It's those people who sell shovels and who are called Levi Strauss and sell blue jeans. So I think it's much more fun when this is not so clear, and then there is room for all this speculation, and so this is a much better time than the time when everything is dead clear and you just have to strive ahead and where the road is clear.
I think that's a very correct comment. And of course, I also, just like you, Gerd, feel that we are striving ahead and we are in the perfect time. One of the best students I ever had is still an active student with me, and he's really, really super smart. So I said, now we have to find a good place for you to go as a postdoc. And he said, well, I don't think I want to stay in this quantum information business. It's actually quite an old field. It's been around for some time, and I fail to see the real progress. and he's smart, and he's going to have a wonderful academic career. He sees action in classical biology right now, maybe as being a super exciting field. So I guess that while we are playing along, it would be nice to see the progression in the way that we are playing along. Now we see the flagship, and we have big political discussions in all European countries, I'm sure in Israel also, about the co-funding and who's going to be the actors, how are you going to involve the industry. And I can see that the politicians who enter this debate now and the industry people entering this debate, they discover quantum computing for the first time. They think it's fantastic. They go on TV and say, wow, we can build a quantum computer and it can factor big numbers using superposition. And they don't know that this is something that was said already 20 years ago. And so it doesn't reflect upon the evolution that's actually happening. Yeah, please, Gerd.
I just want to make another comment because you mentioned the industry. So industry in different countries is different. So there's also industry in Germany. So we've been talking to the industry in Germany, and some are thinking, yeah, this could be interesting, but they have one major issue. I mean, basically all of them say, what we would like to have if we engage ourselves in this, we understand that some of the goals may be 10 to 20 years away. You know, this is too long time scale for us. But still, if this is a worthwhile goal, we are willing to engage ourselves in this, provided that every 2-3 years something comes out that we can market a little bit. So they were very happy about quantum-inspired engineering, because then they thought, okay, so this sounds easier. Maybe we can get something out. So we have to play this this game to increase their appetite and
yes.
Tell them some of the steps where they can go. And if you want to go in this direction, that's of course a challenge to get them all on board.
Right. Well, I think there's a lovely story. So I heard what was the first commercial application of the transistor. So today, everybody has 1 billion transistors in his or her pocket. But of course, it was not 1 billion transistors from day one. At the beginning, it was a transistor the size of a fist. So what is the use of a single transistor the size of the fist? It was a huge success, and it was sold in millions just after a few years after it was discovered as amplifiers in hearing aids. So hearing aid went from being a 6-kilogram battery pack that you would have to carry around with some tube amplifier into becoming the transistor-based amplifier. So the sensor, which is sitting down here, maybe bottom rank on this list, is really one of the things that we should push. And of course, in German industry, there's a proud tradition for Bosch for making sensors. They measure exhaust from Volkswagen cars, and they can measure many things precisely. And we do look forward to. Even at very low levels can be measured by the Bosch devices. So that's good. Well, sorry, Gerd. No, it's true. We have to be creative, and we have to engage the industry. It's a little bit depressing as a European to see American industry running faster than the academic world, and seeing a European industry which is lagging behind the academic world and being more reluctant. But I learned that the reason is that these American companies have billions and billions and billions of dollars, and they don't really know what to do with them. So that's why they might just take the chance, as you said in your presentation. If they fail, they have failed before. But you want to be in if it works. So, yes, please.
So it seems like you mentioned something that's very important, and that is that a single transistor made a huge difference. And then from there, adding 2, 3, 4, every time you gained a lot. But it seems like in the case of the quantum transistor, it's not really happening, because a million classical transistors simulate so much better what a single quantum transistor can do. And it seems like this is a bottleneck that we don't know really how to break through.
But I think the nanocrystals with NV centers, I mean, these probes, and which we also heard about here, there was also the sensing of the frog nerve signals. I mean, this is the direction. Of course, it's already super, super advanced compared to the hearing aid device that you could wear on the beach. But I mean, all the engineers I know who got rich, they got rich by making a ridiculously little device that had to be sold in billions of copies, not by making a fantastic device for which there was almost no market. And so, I mean, it's maybe the next mirror mount you make is the one that's going to make you rich. But is that quantum? No, but it's true. I mean, what you're talking about is this problem that the quantum computer is not going to do interesting things for us before it outperforms the classical one, and that we are still far from that. Yes, Lev?
Yeah, I'm just trying to. I see this discussion goes the wrong direction because you know, we started with Yehuda Naveh, who you know, described a beautiful effort of IBM with the huge money invested into that. So, and then he sort of expects from us to hear enthusiasm that goes away. So now what I see here is just sort of, you know, we try everything and we failed. So most of the comments coming from the scientific community going into the direction, so we sort of fail everything, so don't expect from us anything else. I would expect different comments.
No, thank you, Lev. I think that, I mean, we should at least show our appreciation of being invited here by the Quest Center by actually giving them something positive back, right? So we have 15 minutes, and to compensate for all the bad things that were just said. I don't think it was so bad, actually, Lev. I think that we heard interesting challenges ahead. But yes, please, Gerd.
So I think it's a little bit unfair if we say that, you know, nothing came out of the field. If I remember, you know, usually when you know, you think about what did you do the last few years, we usually come up, you know, we usually find that the things we did, we could not think, you know, the things we write up for a grant proposal at the end, you know, for the report or the grant proposal, had nothing to do with what we wrote in there in the beginning, because in the beginning we did not dare to think about that we can do that. No, one thing, and the other thing is that, you know, working on building these complex quantum machines, these complex quantum physics, is extremely, you know, complicated. And I think in the beginning, many of the things were totally blue-eyed, you know. I remember when we first started to work on the quantum repeater, there was this beautiful DLZ scheme, and everybody thought everybody will solve it. I still remember the conference, which was a workshop in Obergurgl, where Misha Lukin, myself, Niklas Jezin, and Jean Potzig were sitting somewhere on the backside, and there was a young guy working with Peter Zoller giving a talk, you know, and telling us exactly what you need, you know. And we were sitting there and looking at us and said, you know, we were so proud of what we could achieve, yeah. And we thought, you know, this will go nowhere, you know. So, but even though you achieved a lot of things, the systems are much, much more complicated than you really think if you put them in the real world. And I think it's not, I think, don't see it as a negative part that we see you didn't achieve it. I think we achieved an enormous amount. We achieved a really enormous amount in form of the community, yeah? In all fields. I mean, if you would have talked to somebody, you know, when Rainer came to Innsbruck, it would have told him that he can do something with 20 ions at 99.995%. He would have said, no way, yeah? We have achieved a lot of things, but the whole task is much, much more complicated than we thought. And especially because it's not pure engineering. It's not like, okay, you have a roadmap and you go there and you do it. If you build a rocket that goes to the moon, you know what you do, yeah? If you try to build these things, you simply don't know what you do, yeah? And in that sense, I think one has to explore much more, and I think the progress was enormous. You know, I mean, you can kill me now because I said that, but I think it was enormous, even though, you know, we didn't build the quantum computer. But let's face it, who thought about it? We're going to build it right away from the beginning. Nobody.
I think that's absolutely right. And in fact, when I referred to politicians saying the same thing as we did 20 years ago, it doesn't mean we say the same things as we did 20 years ago. I think we fulfilled our promises roughly. I mean, all the time plans, well, will we be in 5 years and 10 years? I mean, we didn't promise 100 iron computer at that time, and we don't have it today, but we are getting closer to all these milestones. But we just have to remember as a community that it's not the easy ride anymore. We should, of course, the promises we make today or reflections upon our field should also reflect 20 years of experience. And even though it's comfy to sit under the shoulders of a minister who says, and you will factor big numbers, and you can use superposition principle, we should inform that minister that he should expect a little bit more from us, or at least he should ask a few more people what this field is really about. Because we don't want to cheat the community, and we don't want at least be caught cheating the community a year later when they realize that we didn't do exactly that. Yeah, please.
So against this 20 years ago, so this is the question to Yehuda Naveh actually. So he mentioned in his talk 17 years. So I'm just interested in what does this mean in 17 years? Why do you always, your future is measured in 17 years from now?
Answering the question what will happen in 17 years, I just don't remember myself saying anything about 17 years. But let me share one experience I had yesterday. We were around 25 people sitting in Paris, and very different people, but all of us had one thing in common. We had interest in quantum computing. And some people came from industry, some from academia, some were experimentalists, some did cyber, some did quantum internet, and some did. And then actually it was my initiative. I said, let's define 4 very crisp goals. One of them was factor 2048-bit number. Another was, we defined 4 very crisp goals. And then we asked anyone who wants for each goal to write down just the year that it will happen. It's something very measurable. And we had, not everyone participated, but we had like 15 results for each of the 4 goals. So it's like 60 numbers. And the interesting thing was the spread. There were 2 interesting things. First, there was not even one goal where even one person wrote infinity, meaning it wouldn't be done. So everybody believed that all the goals will be reached. But the second interesting thing was the spread. So for each one of the goals, the spread was like probably average was maybe 30 years from now, but the minimum was 5 years, the maximum was 70, 80, 90 years from now. And this is the community, which this is their, this is how they bring bread home. This is their, this is what they do for life, doing quantum computing. And there is absolutely no consensus on where this is, what is going to be the pace.
While you pass the microphone to Dieter, I have found a correlation that most people predict it to happen just after they retire. So that's part of the spread. Please, Dieter.
I was thinking about Avi's remark with whether there is any instrument. Maybe there is one. I think the simplest quantum device which we have been using since the 50s is an atomic clock. And so I think we are going to have, or we already have, atomic clocks which have a total size of a cubic centimeter, including everything and so on. And my personal view is also, when I try to explain, is the quantum computer is the VLSI version of atomic clocks. It's running a huge number of atomic clocks in parallel. And so maybe there is something of this kind, but just the complexity is growing very much. And also in terms of the gold X, it's like a threshold problem. So, and we have no idea where the threshold is or so. But it's very interesting to find out whether it exists at all.
Yes, Gert.
I wanted to make a remark about this being a negative feeling for the center now it is starting. So first of all, I think if companies like Google or IBM start investing and trying to build something, this is nothing that we can compete with. And it's also nothing that we want to compete with. But it's something that our community has triggered, so this one can be proud of. But all indications are that this whole field, and with potential applications, is still at the very beginning, and there are many things out there that we cannot dream of now. And a center like Quest is exactly, I would think, for my taste, a center like Quest here at this university has actually that purpose, to explore this potential future, try to think things that have not been thought, and then surprise, surprise, something comes up. If you bear with me for a minute, I would like to read to you the 3 last sentences of a book that I like. It says on page 352, which is the last page, the last part of this work gave results that did not at first appear to be capable of useful application to the life of man until quite recently, when an apparatus has been constructed of preeminent practical importance. It is the task of science to strive after truth without having any secondary object in view. If it remain true to this ideal, the practical applications will fall into its lap as the ripe fruits of knowledge. And you know when this was written? 1875. So they had similar problems, justifying to the sponsors. but I think the real big steps ahead always required people to think something which was not related to any application which people had in mind at this particular time.
Yes, yes. Thank you. Michael.
Yes. So I hesitate to speak about that because, well, I don't want to say stupid things, so I prefer not to speak. But then I thought about it, and I would like to give you several elements of thought. First thing, science never changes in a linear way. So we can look at the evolution of even superconducting qubits. The story of superconducting qubits is a story of revolution. So you have a stall, and then you wait, nothing seems to appear, and then, how to say in English? Pitom. Yeah, there is something which happens. Okay, so first thing. So science evolves by revolution and not by evolution. Even though during that period there has been a lot of evolution which allows to give rise to the revolution. The second point is the point that even revolutions do not appear always immediately. I take the example of Planck, who made the discovery of quantum physics, and this is the reason why everybody here is here today. I think it took 5 years to publish a paper which sustained Planck ideas. And I think the first one who wrote an article who is supportive about Planck ideas is Einstein. And even 6 years after that, when Einstein came to ask for Planck for a recommendation letter because he needed a recommendation letter, in this recommendation letter, Planck wrote, well, Einstein is a good guy. He made a lot of good things, Brownian motion, relativity, but well, of course, there is a small, I would say, mistake about this story of quantum physics. But I mean, even Planck himself did not recognize that what did Einstein was in fact a big jump. So it takes time, even for revolution, to appear in science. And the third point is that also I'm referring to the past. When Thomson discovered electron for the first time, journalists came and asked him whether what would they do with this electron. And you know what he answered? Probably nothing. So if I want to come back to the big challenges that I see here, I would say the following. On one hand, we have a problem of error correction, which will be a big problem, especially for the qubits which have small lifetimes, small relaxation times, small coherence times. On the other hand, we have very nice qubits, very nice systems which can live forever, but cannot speak with each other, and are in a way as useful as a standalone telephone if you want to build a computer. So that's why I believe that hybrid is really a an interesting subject. Even if we do not know exactly how it will appear, it must appear. That's it.
Good, thank you very much. We are nearing the end of this discussion. You haven't, yeah, that's the microphone coming.
Related to the question Emmanuel asked about technology, I also have a historical quote. A delegation, it's probably an urban legend, but I think it's relevant. A delegation was visiting Michael Faraday's lab to see his progress, and he showed them all his Faraday effect, all his motors and conductors, and they asked him, what's it all going to come to? He says, I don't know what will emerge, but I'm sure that one day you'll be able to tax it.
And with the overhead rates we
so
pay...
there's going to be a quantum industry,
yes.
There's going to be quantum technology, and they will be able to tax us.
Right.
But, and that's part of life, and I think it's a good thing that we shouldn't be worried about, because the feedback between technology and science is what has driven our fields, quantum optics. Without the laser and all its technological marvels, semiconductor, all the connections have driven basic science to where it is today, and vice versa.
I think that's very right. And with the overhead rates we pay at most universities, we are already getting tax from the money that goes into the quantum research. I think in addition to being open to the physics technologies, I mean, just to summarize this discussion, we are doing that with the best of academic tradition, with a patience and also an eye for opportunities. I think that your comment about the golden eggs is an important one, and maybe also just recognizing when do we have a golden egg. And I think you had your heuristic comment in your presentation before. I think that taking the goals not too literally, taking the applications not too literally. We heard Neil Davidson's talk this morning about solving some minimization task. Maybe we shouldn't think as much as a physicist who wants the real minimum, because that's the only thing that matters. We just want a better minimum than the other algorithms do. And a deeper minimum. And if we can do that, also in the spirit of you said with doing chemistry or pharmaceuticals with a quantum simulator, it doesn't have to do the right thing. We have to test it on some rabbits and rats and later humans anyway. But if we do better than what we can do with the current technology, then we have the competitive advantage that can push these things. And that's maybe not exactly forecasted in the way we normally talk about the quantum computer or quantum simulator. So there will be space for theorists who can think like that, and not only for theorists who can make the next gate. Are there last important additions? If not, I'd like to thank everybody. I hope that our Quest colleagues ended up on the happy note after the gloomy beginning of our panel discussion. Thank you very much for participating.